Welcome to Math 331, the little problems. This is going to be lecture 30, and we're going to continue doing some PutnamA1 problems ready for the upcoming Putnam exam. And so one of them, this is not a Putnam problem, but this is a problem that I created a while ago that I really liked back when I was an unofficial TA for discrete mathematics at Princeton. We define the coloring number of a graph of V vertices and E edges to be the smallest number of colors such that no two vertices that share an edge are colored the same. So out of curiosity, has everybody seen problems like this? Coloring. One of the famous, the four color theorem is if you have any nice region in the plane, only four colors are needed. Does anybody know which US state could have caused trouble? Michigan. Why does Michigan cause trouble? It's split into two parts. Now, fortunately, it's okay, but Michigan is disconnected. So consider the following graph. The vertices of the integers 2, 3, 4, all the way up to 10,000. Two vertices are connected by an edge if and only if they share a common factor. So there's no edge between 2 and 3, but there is between 2 and 6, between 3 and 6, none between 2 and 5, and so on. And I want you to prove that the coloring number is at least 13. So what does it mean for the coloring number to be at least 13? Well, one way is, can you find 13 vertices that are all connected? And you have the numbers from 2 to 10,000. Can you give me 13 numbers that will all share a factor? And so, of course, whenever you see a problem like this, which numbers do you focus on? Well, this primes, but which numbers in the problems do you think matter? 10,000. And what else? 13. So the real question is, with 10,000, I have 13. How would the 13 change if I change the 10,000? Can you think of any relationships between 13 and 10,000? We're trying to find at least 13 vertices that are all connected. Any thoughts? Well, 13 factorial would be huge. And again, if you did 13 factorial, you would have things connected with 13 factorial, but they wouldn't necessarily be connected with each other. So for instance, if I have something over here that's red, I could have two things colored blue if they only connect to the red, because they don't connect to each other. So can you give me 13 or more vertices that are all connected? So again, if I give you, I'll do a complete graph. And we'll probably do it on, we'll do it on 4 colors. So you can see blue is connected to everything. Black is connected to everything, so I need to draw these extra lines. Green is connected to everything. So this is a complete graph on 4 vertices. Because everything is connected to everything, I need to use 4 colors. If I didn't have a complete graph, if I gave you instead, something like this, or imagine these are the connections. Well, if you notice that in the top, I have a complete graph. So I have to use 3 colors here because they're all connected. And then, can I get away with a new color? Or do I need to use one of the old colors? And so I could put a red here because it's not connected to red. So one way to show that the coloring number is at least 13 is to find 13 vertices that are all connected that give you a complete graph. So this would be called K4 for the complete graph on 4 vertices. So can you find a K13, a complete graph with 13 vertices? So you've got 10,000 and you have the number 13. Can you think of 13 numbers that all share a factor?
First, 13 even the first thing.
Good. So you actually got, so in fact, instead of just doing the first 13 even numbers, you could do all the evens, right? So if you do all evens, it's at least 5,000. What a lot of people do is there's another natural set of 13 numbers that all share a factor. So you all have not found it. Yes. So you could do 2, 2 squared, 2 cubed, dot, 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 all the way up to 2 to the 13. And so a lot of people see that and they say 2 to the 10th is 1,024. So this is 8 times that. So it's going to be less than 10,000. So it's a little bit more than 8,000. I could have made the problem a little bit nicer. Rather than 10,000, I could have done 1025, right? And had a culling number of at least 10. So if I did it like that, I think it would be really highlighting the fact that you should be looking for powers of 2. Or I could even do the 1024 rather than 1025. And so if you look at it like this, you will clearly see the powers of 2, but that's not the best answer. If I use all the evens, it's at least 5,000. And in fact, it's at most 5,000. At most 5,000. Color 2n and 2n plus 1 the same. So no adjacent even and odd number share a factor once you're beyond 1. So 6 and 7 don't share a factor. 8 and 9 don't share a factor. So whatever color you color an even number, color the odd number next to it the same color. So you only need 5,000. So you can do far better than just show that the coloring number is at least 13. You can actually prove that it's 5,000. But what I like about this problem, and I know I'm being recorded, is I confused myself when I wrote this. I wrote this thinking of powers of 2 and thinking that's you're going to get 13. And I completely missed the even numbers at first. And a lot of students over the years have gone to powers of 2 because of how it's written. And so I wanted to talk about this problem today because a lot of times people try to get you to look at a problem in a certain way. That may not be the best way to look at it. And so just to be aware. Okay, so here are a couple of Putnam problems. And so I just chose a few semi-randomly. I have not really looked at them, to be fair. So if n is a positive integer, define f of n to be the sum of the first n factorials. Find polynomials Pn, Qn such that Fn plus 2 is Pn Fn plus 1 plus Qn Fn. The second one is x and t and y of t are real valued functions satisfying the following system of differential equations with initial conditions x of 0, y of 0 equals 1. Find x of 1 plus 3y of 1. And then there's a nice parenthetical remark. So these were proposed problems or potentially proposed problems. Some of them actually were problems. For this proposed problem, it says, this problem was later withdrawn for having an easier than intended solution. And so, again, I have not solved these problems. I have not really thought about them too much. But what is one way you could solve this problem? So this is similar to the cosine problem we did last time. One way you could have solved the cosine problem from before, and again, one of the nice things is I can actually just, I think, toggle back to the cosine problem. Yes. Is you could actually find the derivative of the derivative, and then evaluate that at 0. We don't need the derivative. We don't need the second derivative in general. We only need the second derivative at 0. So what I'm trying to do in this class right now is emphasize which perspectives are going to be the most valuable. It's a game. It's an adversarial relationship. Think of it as a magician. They're trying to get you to look at the wrong thing. And so I got to see some magician secrets over the years, and just some things that they can do to get you to look at the wrong thing. They love to do that. Your instinct is to say, well, I know how to differentiate, and I know how to differentiate twice, so let me calculate the second derivative. That's not what's asked. What's asked is you want the second derivative at 0. So that's all you need. Now, one way to compute the second derivative at 0 is to compute the derivatives beforehand. If you ask me, which kid is my favorite, I of course do not answer that. When they were young, it was whoever slept better at night. But now they're old enough that I can't say which one I love the most. Okay. But there's a reason I was saying this. When you take multivariable calculus, you hopefully do Lagrange multipliers. Good. So you have this extra parameter lambda. Do you care about lambda? No, you just introduce lambda to solve for the potential candidates, for the potential points to be maxima or minima. At the end of the day, you care about the points. And so a lot of times you actually never find lambda. You often take ratios of equations and the lambda cancels out. And it's just a helping variable along for the ride. That's how you should view a lot of these things, is that one way to do these problems might be to compute certain things, but they may not be needed. So when I see that this problem is later withdrawn, my first thought is there's probably a way to find just maybe x of 1 plus 3 y of 1, or if not that, to find maybe x of t plus 3 y of t without finding x and y. And so if you look at the problems, I'm going to assume that that's not x of t, that it's x times t. Do you see any nice way to get x of t plus 3 y of t?
dx dt y1 plus like 3 times dy dt. Then like we get like t times 2t times
Okay, so what do you want to multiply the first one by?
1.
By 1? And what do you want to multiply the second one by? Okay, so we multiply the first one by 1 and the second one by 2. Then we would have negative x plus 2x would be x.
Sorry about that.
We multiply the second one by 3. So we multiply by 3, then we're going to get a 2x for the first one, and we're going to get a 6y for the second. And so when you do this, it's going to give you something like a 2xt plus 6yt plus ... which is 2x plus 3y. I'll do a 2t plus ... Oh, well, and then over here on this side, we'll just have d by dt. Oops. So instinctive to do d by dx of x plus 3y. And so if you do that, we can actually solve for that very easily. So this is why I think they probably withdrew the problem. I think they wanted you to find x of t, y of t, and then take that combination. But my feeling is you might actually be able to just come up with a really nice solution just by playing it like this. I don't know. I haven't looked at these problems. But it's a great example of answer the problem that's asked. We're not trying to get a complete understanding of x and y to be used to understand its trajectory. We just have to answer this one specific question. Okay. Problem A1 or B1, inscribe a rectangle of base B and height h and an isosceles triangle of base B and a circle of radius 1 is shown. It looks like it's cut off the problem. What do you think the problem would probably be? I have a guess as to what the problem would be. It seems like I have pasted and lost some of it in the pasting. So what would you guess the problem is? So I'm sorry.
Inside the upper.
I'm sorry.
Maybe this triangle T is somewhat inside the.
Oh no, I'm sorry. Sorry, this part over here is for the next problem.
Okay.
So for the top one, what do you think the problem is? What ratio? Well, you can choose any H and B that you want within reason. I can think of two natural problems.
Maximize the area.
One is maximize the area. That's what I would have gone with. What's the maximum area? What they said the problem is, when do they have the same area? So what HB give the same area? So both of those would be natural questions to ask. And the last one is, let's let T be a triangle and R and S are rectangles inscribed in a triangle as shown. Find the maximum value or show that no maximum exists of the area of R plus the area of S over the area of T. And so T ranges over all triangles and R and S over all rectangles as shown. So we're not given a specific triangle. We're allowed to vary over any triangle we want. So which problem do people want to look at? First one, okay. Let's look at the first one. Okay, so if n is a positive integer, we've defined fn. Find polynomials p of n and q of n such that this is true. So this is supposed to be an A1 or a B1 Putnam problem. This means you should be able to do it, right? You have a chance. So another way of looking at it is you have 3 hours to do the first section. If you can get this problem in an hour, is that a good use of an hour? Absolutely. If you can get this problem in 2 hours, that's a good use of an hour. And I'm sorry, a good use of 2 hours. If it takes you 2.5 hours, well, maybe you could have done something with one of the other problems. But I wouldn't be afraid to spend a couple of minutes just trying to explore this. So how might you start?
Compute like the first few values.
Yes! Gather data, right? We have an hour, right? Gather data. So what we should do is, here's n, here's f of n. I'll do f of n plus 1, f of n plus 2, pn and qn. Now the problem is I don't know if we can figure out what pn and qn are. Okay. So I'm going to, okay, they say for n greater than or equal to 1. So we'll go 1, 2, 3, 4. So f of 1 is going to just be 1, right? F of 2 is going to be 3. The next one is going to be 9. And then 23. Yes. All right, so then Fn plus 1 would be 3, 9, 23. And then after 23, we have to add 4 factorial. We have 5 factorial, which is 120. So it becomes 143. And then Fn plus 2 is going to be 9, 23, 143. And then after is 720. So it becomes 7, 8, 6, 3. And so the question is, what degree do we think these polynomials are? So one thing is to try to think about how quickly things are growing. Let's get some order of magnitude estimates. When n gets really, really large, how big is Fn? So we'll do this as an aside. So Fn is 1 factorial plus 2 factorial plus dot 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 plus 3 factorial, plus n factorial. How big is Fn? Can you give me like a rough estimate? Gun to your head, approximately how big do you think it is? I need an answer now. I need an answer. Well, no, just give me an estimate for Fn. It can be in terms of factorials. What's the simplest approximate? You know? If n,
it's going to be much bigger than n factorial.
okay, so we know it's clearly smaller than n factorial, right? I mean, sorry, I'm sorry, we know it's not smaller than n factorial.
It's bigger, but it's not much bigger, I think.
Right, so the question is it roughly of size n factorial? So we know n factorial is less than equal to f of n, is less than equal to n factorial, plus then we have n minus 1 factorial, and then we have n minus 2, et cetera, et cetera, et cetera. And then this over here, n minus 2 factorial times n minus 2. I might go one more term, actually. Let me go one more term. Plus n minus 3 factorial plus dot, 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 all the way down to plus 1 factorial. So this is going to be less than equal to n factorial plus n minus 1 factorial plus n minus 2 factorial plus n minus 3 factorial. And then how many terms do I have from n minus 3 downwards? I have n minus 3 terms. So if I replace everything with n minus 3 factorial, I've only made things larger. So this is a really common way to estimate things. And what I'm doing is I'm just leaving myself a couple of terms in the beginning, because if I kept all of them, then rather than the n minus 3 factorial, I'd have an n minus 2 or an n minus 1, which is larger. Well, what's n minus 3 factorial times n minus 3? That's basically n minus 2 factorial, right? So this is basically less than equal to n factorial plus n minus 1 factorial plus n minus 2 factorial plus n minus 2 factorial. So that's n factorial, and I guess I can do an equal sign here. Plus n minus 1 factorial plus 2 times n minus 2 factorial. So this would be n factorial plus n minus 1 plus 2 times n minus 1, I'm sorry, n minus 2 factorial. So this would be n factorial plus n plus 1 times n minus 2 factorial. Yes?
That's basically n minus 1 factorial.
That's basically n minus 1 factorial. So we can write this as n factorial plus n minus 1 plus 2 times n minus 2 factorial, which is n factorial plus n minus 1 factorial plus 2 times n minus 2 factorial. I mean, I just went back to where I was. So, but this is basically going to be less than equal to n factorial plus 2 times n minus 1 factorial. So we know that Fn is really not much more than n factorial. So when we try to get a sense of the size, this is going to be about n plus 1 factorial. This is going to be about n factorial. This is going to be about n plus 2 factorial. So if we look at it, it's possible that our polynomial could have degree 2024, right? And that everything just miraculously cancels. But how much larger is Fn plus 2 versus Fn plus 1? N times. Basically n times. And how much larger is it than Fn? N squared. So maybe if I'm looking at this, I might think maybe Pn is degree 1, Qn is degree 2. And that would get everything to be roughly of the same size. Again, I don't care what the answer is for this problem. I care about thought process. And if you have other ways that you're thinking to attack this, please. I have deliberately not looked at this. So this is just spending a couple of minutes, getting a quick feel for the size of things, gathering some data, and then trying to see, can we look at this data somehow and come up with polynomials? So degree 1, that means unfortunately 2 terms. Degree 2 would mean 3 terms. We might have, some luck with maybe the higher order terms. Yeah, it's possible that maybe they all don't have the same degree. Maybe the Qn is lower. Maybe the Pn gets the main term to agree, and then the Qn, fixes things. So this is just trying to get a feel for what the answer is before I do too much work. Looking at this, there's no guarantee that it'll be the case, but maybe Pn is degree 1, maybe Qn is degree 2. But I could bump them both up, and maybe there's just catastrophic cancellation. Maybe Pn has a positive sign, Qn has a negative sign, and so maybe things perfectly cancel, and the main terms vanish. And does everyone see how that could be the case? So looking at the data, I could try to put down polynomials. I would have 5 free parameters. So how many data points would I need? If I want to solve them, I need 5 equations, right? I've only got 4 right now. So I would need to do 1 more. And I would need to solve this by hand. It's not pleasant. If it works, there is a chance I could probably crunch through that in an hour. If their degrees are higher than 1 and 2, then I'm in real trouble. And the factorials grow so rapidly that the numbers in the equations are going to be painful. So the other way to try to look at this, it should still be copied, is to just plug some things in. So we would have n plus 2 factorial plus all the way down to plus 1 factorial is Pn times n plus 1 factorial plus all the way down to 1 factorial plus Qn n factorial all the way down to 1 factorial. So we would get n plus 2 factorial plus all the way down to 1 factorial is going to be, and now the question is, how do we want to deal with things?
We're talking about uncommon numbers, P and Q, right?
Yep.
Is there only one possible solution, or could there be many?
My feeling is there's probably only one solution. Sometimes in something like this, the question is there a nice relationship between fn plus 1 and fn that would give you 0? Because if so, then you could plug that in.
Like, where's it like, it wouldn't be one, but I think you could set, let's say, like Qn equal to 0 and Pn equal to n plus 2.
Good. So I was actually thinking about starting with Pn equals n plus 2, and that would fix the first term. So if we write Pn as n plus 2 plus, let's say, maybe little p of n, then you would get n plus 2 factorial plus n plus 2 times n minus 1 factorial plus n plus 2 times, oh, sorry, that would be n plus 1 times n factorial plus dot dot dot, and then plus, you would then have, p of n times n plus 1 factorial plus dot 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 all the way down to 1 factorial. And we would also have the q of n times n factorial plus dot 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 plus 1 factorial. I mean, just,
I think if you can make Q times f of n equal to n plus 2 factorial.
right, so that was the thing, is if you could make that equal to n plus 2 factorial, then you can take q of n to be 1.
Yeah.
So can we make Pn times Fn plus 1 equal to n plus 2 factorial plus dot 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 plus 1 factorial?
Or we can do the other thing. I think if we make P to be equal to 1, then we'll have P times f of n plus P times n plus 1 factorial.
So then you would need q of n times f of n to be n plus 2 factorial.
Yeah.
Or can we make qn fn equal n plus 2 factorial? So I mean, if wait a minute, we're making, if we want Pn Fn plus 1 to be n plus, I think I wrote the wrong thing. If we want Pn Fn plus 1 to be n plus 2 factorial, I think, plus n plus 1 factorial, and then you could just take q of n to be 1. And then the other one is, if we can make qn fn equal n plus 2 factorial, then we would be done. So do we think we could make qn fn equal to n plus 2 factorial?
It comes to math, it's probably some kind of, I don't know, term on terms depending on n, then minus 1, so all the canceling there.
So you would want to have q of n to have some quadratic, maybe, because we've got to get up to, so we would want, the leading term has to be 1, so it has to be like, n squared plus an plus b times n factorial plus n minus 1 factorial plus dot 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 plus 1 factorial. And we wanted that to be n plus 2 factorial. So that's going to be so if we take a equals 2, n squared plus an is n squared plus 2n. Oh, it's not going to be quite right. I was thinking we can write, you know, a quadratic maybe as a n plus 2 times n plus 1, so that when it hits the n factorial, it's right, and then everything else is going to hopefully cancel. But I think along those lines, it's no longer letting me paste. Whenever you have something like this, you want to have lots of cancellation.
Yeah.
So we want to solve fn plus 2 equals pn fn plus 1 plus qn f of n. What can I replace n with? There's two good things to replace n with. I have this relation that I want to be true for all n.
So, do you want to see some data, or do you want to?
Well, we've already looked at data, but this is supposed to hold for all n. And notice we have n plus 1, we have n plus 2. So what might be useful to replace n with? N plus 1 or n plus 2, or maybe n minus 1. This relationship is supposed to hold for all n, right, greater than or equal to 1. So we could replace n with n plus 1, so we would get fn plus 3 is pn plus 1 fn plus 2 plus qn plus 1 fn plus 1. But we know what fn plus 2 is. Right? It always makes me feel good when I hear something like that, you know, maybe we're on the right track. So what could we do now to both sides? You know, if we subtract the fn plus 3 minus the fn plus 2 is going to be very nice. Right? That would just be an n plus 3 factorial. Yeah. You know, if we look on the other side, things become a little bit nicer if we multiplied by maybe you know, the first one by pn and the second one by qn plus 2, then the fn plus 1 terms would cancel. But then you have all these different things coming in. And so it's not immediately clear to me what's the right thing to multiply by, but the hope is that if we now subtract, you know, we're going to get things very nice. And so now if we subtract, we would just get n plus 3 factorial is going to be, we have an fn plus 2 term, so it's going to be a pn plus 1 fn plus 2 plus p of n plus qn plus 2 fn plus 1 plus q of n fn. And again, I'm not sure if this helps. You really want to take a combination so that a lot of things vanish. And we really haven't gotten too many things to vanish. We could substitute in the fn plus 2 and the fn plus 3, or we could go in the other direction. So the next thing is, rather than going up, we could have gone down. We could have had, we could have had fn plus 1 would be pn minus 1 fn plus qn minus 1 fn minus 1. And maybe we keep going all the way down until we get to an f of 1. And so we could substitute in fn plus 1 above. And if we substitute, this would yield fn plus 2 is going to be pn times pn minus 1 fn plus qn. I think that's the fn term, plus qn minus 1 fn minus 1. So again, I don't know if any of these work. On Monday, we'll actually talk about, which way it actually works. So I'll think a little bit about this over the weekend, and I'll let you think about it. But it's just, how might you try to attack a problem like this? If you have some inspiration to try to write down what the polynomials might be, you could try to play games like that with small values. If they're quadratic and linear, the danger is always that you could have things canceling. And so you could have things of maybe a higher degree. But there's a lot of problems where you have this massive cancellation in the middle by doing a telescoping sum. And the hope is that we have something like this, is that we can write fn. I'll say this is the last thing, is fn, or maybe I'll do it this way. Fn plus 1 is fn plus n plus 1 factorial. Fn plus 2 is fn plus n plus 1 factorial plus n plus 2 factorial. Conversely, of course, we can write fn plus 2. Right. So we could write everything in terms of fn. Right? So rather than looking at fn plus 2, is maybe what we do is we replace fn plus 2. Maybe we take this and we put this in here for fn plus 2. And then we take this and we put this in here. And now we just have everything in terms of fn. And you'll have a couple of other things floating. So I don't know which way works, but this is an A1 problem. It's worth the time to spend a couple of minutes, thinking about all the different ways, and then see if one of them, leads to a solution. So I have no idea if any of these work. I'm hoping at least one of them will work. If you put a gun to my head, I would ask you to lower it. But if that's not an option and I had to answer, if I had to choose, I would probably say my gut instinct, and I know this is being recorded, so this is dangerous, is probably to go maybe with the last thing and just try to replace everything in terms of fn.
Just trying to guess.
Yeah. Because then you would hopefully just you'd have a couple of like n plus 1 factorials and n plus 2 factorials. If I had to, does anybody have any method that they think is particularly?
That's probably what I would do. I'm not sure what I would do.
I'm doing something different, but I don't think it's going to lead anywhere.
What were you doing?
Q times f of n, we need to make it equal to n plus 2 factorial. So
right. So the question is there a way to solve it by having one of the terms being nice?
And then I said, okay, if Q is something of the form n plus 1 times n plus 2 minus something.
Yes, yes.
And
That's a good way to start, is to have some part of these functions being something that's nice, but then you can get so many cross
but then
checks.
it gets kind of ugly.
Yes, and that's the problem.